Good morning, ladies and gentlemen. The next topic for electrostatics is about electric fields themselves. We've already spoken about Coulomb's law, but when we talk about Coulomb's law and compare it to most forces can easily be referred to as contact forces because, well, obviously we see the contact. When there's a person pushing on a box, there's contact. But gravity and electrostatic force are both very different because we can't see the contact at all. So in order to better imagine what electrostatic forces look like, we came up with the idea of an electric field. An electric field is very similar to our idea of a gravitational field. Okay, so if you think about what with the Earth, the gravitational field is, well, always pointing towards the center. And gravity will always point towards the center. And if you're caught within this gravitational field, you're going to feel a force downward. But there's one key difference between gravitational forces and electrostatic forces. Gravity is always going to be an attractive force, meaning that anything has mass will attract to another object that has mass. There's no such thing as anti-gravity where the masses will actually repel from each other. So gravity is only attractive, but electrostatic forces can be either attractive if they're opposite charges or repelling if they're like charges. So whenever we talk about the electric field lines for charges, we always have it going out of positive and into negative. Okay, so rather than just one type of field line, we have, well, two basic rules now for field lines. So if you were to draw that yourself, the strength of this electric field is determined by where the lines are closest together. And you can obviously say that if these lines are radiating outwards, it's always going to be strongest right near the charge, as opposed to further away when the electric field lines are more spread apart. Also, one key rule to remember, when drawing electric field lines, the electric field lines will never cross each other. But the thing is, what if we have more than one charge? Just like when we deal with the Earth and the Moon. We know the Earth and the Moon both exert a gravitational force. And the dark area around the Earth and the Moon show where the gravitational force is the strongest. But if you look carefully, there's a spot right here that's light colored. Well, that's because the gravitational field lines from the Earth and the Moon are canceling each other out. Normally, the Earth has much stronger gravitational force because it has a lot more mass. But if you were to put in a little astronaut over there, there would be no gravitational force because he would be pulled towards the Moon and towards the Earth at the same time. So we know that in that area between the Earth and the Moon, the gravitational field lines are canceling each other out. And this is another representation of the gravitational force around the Earth and the Moon. And you can see that closer to the Moon, the two field lines end up canceling each other out. So we could do that same drawing when we deal with multiple charges. We know that that the field lines are going to go out of positive and into negative. So in this case over here,
electric field.
let's see. Let's go back to this drawing. If you were to draw it yourselves, that means the line's always going to go out of positive and into negative. And the line is going to end up curving because it ends up getting pulled towards that negative charge. So out of positive and into negative. When you have two positive charges, the electric field lines will end up looking like that they repel away from each other. So they go out of positive, and you can see as if they're being pushed away from each other. Because normally it would have looked like a straight line coming out, but those straight lines are getting repelled away from each other. For two negative charges, it's going to look exactly the same, except for the fact that electric field lines go into negative. So in this case, it'll look more like this.
Patterns around charges.
Now, of course, normally we can't see electric field lines, or nor can we see gravitational field lines, but we can visualize it using certain methods. In this case, they used, they used castor oil, petri dish with a castor oil, a high voltage source, and semolina seeds. And they basically have a large positive charge on one side and a negative charge on the other side. And you can see when they turn up the voltage that the semolina seeds are actually aligning themselves along the electric field lines. You can see it's actually going out of positive and into negative. When they use an isolated point charge here, in this case, we have just a positive charge. Now, normally the semolina seeds can't really show direction. The direction is just what we make up ourselves. But we can see that the pattern, we have it creating and being repelling away from each other. Okay. In this case over here, this is a special situation, okay, which we're going to talk about next. Let me pause this right here. In this case, they have two parallel, so they charge one plate positive and one plate negative, and you can see that the semolina seeds are actually aligning themselves in straight lines that go across. Now, the reason that's significant is because all those lines are evenly spaced together. So if we draw it here from another point of view, one plate is positively charged, one plate is negatively charged, and we have those electric field lines going straight down, well, mostly straight. The fact is, the electric field is constant inside parallel plates. Well, there's some sort of bending on the outside, okay? But on the inside itself, the electric field at one point, E, is the same as any point anywhere else, okay? So electric field line is the same everywhere inside parallel plates. And we'll come back to that a little bit later. But the next example I want to show you is about the hollow conductor. When you charge up a hollow conductor, let's say we just fill it up with lots of electrons, what's special about the hollow conductor is that at any given point inside the hollow conductor, those electric field lines are going to cancel out, which means that the total electric field inside is 0. However, on the outside, we are still going to see our electric field lines going into negative, okay? And this is true also for a solid conductor as well. The electric field inside any sort of solid conductor is going to be 0, as the charge remains entirely on the outer edge of the solid conductor. So if I were to draw a solid conductor, this is a small example over here. Okay. The fact is, anytime you put a charge on a solid conductor, the electrons are going to spread out as much as possible. They only reside on the outer edge. And you're still going to get an electric field that goes in, while inside E is equal to 0. The reason that's important is, well, take a look over here. Something called the Faraday Cage. Pretty crazy. Now, the Faraday cage is just an example of a hollow conductor. And no matter how it's charged, over here we have a Van de Graaff generator, which is generating perhaps 1 million or 2 million volts. And when you generate voltage that high, just like with lightning, well, you can see the effects are pretty cool. But the person inside the Faraday cage, he's inside a hollow conductor. And because he's inside the hollow conductor, the electric field inside the hollow conductor is 0, no matter how much electricity strikes the outside. And this is true for any hollow conductor. You're always going to be protected from any sort of electrical strike. Sorry about that. Including in an airplane. In this picture over here, you see an airplane flying through the sky and struck by lightning. In fact, it struck 3 different places at the same time by lightning. But because the airplane itself is a hollow conductor, all the people inside are perfectly safe. And the same is true if you're inside a car. And let's say there's a down electrical line, right? If an electrical pole falls over, it falls onto your car. As long as you are inside the car, you're perfectly safe. It has nothing to do with the fact that your tires are made out of rubber, because rubber honestly will conduct electricity when there's enough voltage applied to it. But because your car is a hollow conductor, as long as you stay inside the car, you're perfectly safe. But if you step outside the car where there's a live electrical wire, then you get zapped. So just keep that in mind. If you are in some sort of high danger area with electrical lines falling, always stay inside your Faraday cage or your car. Okay. Now, ultimately, an electric field is just like a gravitational field, something that exists around the charge. But what's more interesting is what happens when you place another charge inside that electrical field. Let's just go back to our example of gravity for a moment. Right now we have the Earth, and we see our gravitational field G, which is pointing downward. Any object that's placed inside that gravitational field is going to feel a gravitational force. So gravitational field versus a gravitational force. Don't confuse the two terms. Now, is this person's mass the mass that's creating this gravitational field? No. Of course, that's going to be the massive mass of the Earth itself. But any object that exists inside the gravitational force feels a gravitational force. Okay? And the same idea applies to charges as well. Now, before we had Fg equals mg, the weight is equal to mass times gravity. So in this case, the electrical force is equal to the charge times the electric field. Okay, and Q naught just means that it's a tiny, tiny, tiny test charge. Just like I exist as a tiny, tiny, tiny mass in comparison to the Earth itself. Okay, and because this is the formula for electric field, if you think about E equals to F over Q, that means our unit for electric field is simply going to be newtons per coulomb. Okay. So over here we see another example of this. Okay. Over here we have the Earth creating gravitational force G. Anything that's placed inside that gravitational force feels a gravitational field feels a gravitational force. Anything that feels the electric, any charge that feels the electric field will feel an electric force. Okay. And we would apply our normal mechanics equations to this as well. The only difference, again, between the gravitational field and the electric field is that there are two types of electric fields because there are two types of electric charges. They either go out of positive or into negative. So in this case over here, we have a positive charge placed inside another object's electric field. This object has an electric field that radiates outward. So no matter where you put that charge, the other charge is always going to feel a force away. Also keep in mind that since there are two types of charges, there are two directions that the force can be felt. So here we have our parallel plates with our constant electric field. Okay? But notice, the positive charges feel a force in the same direction as E. And it makes sense because it's going to be attracted towards that negative charge. However, negative charges feel a force in the opposite direction of E. Okay, and which again makes sense because the negative charge is attracted to the positive charge on the other side. So keep in mind that you should always be able to determine what the direction of the electric field is simply by knowing what the direction of the electric force is. This is just another example of a positive charge being attracted to the negative plate with a force of QE. Let's actually do a quick practice question with this now. A proton is placed in an electric field. So we'll draw a proton with a positive charge. Now, it feels a force, an FE, to the left. In fact, they tell us that the force is equal to 2.5 times 10 to the negative 4 newtons left. Because it is a proton, you should automatically note that the charge is equal to 1.6 times 10 to the negative 19 coulombs. And they even give us the mass over here, which we'll use later. Whoops, I crossed it out. The mass is equal to 1.67 times 10 to the negative 27 kilograms. So these two are givens that are on your reference table. But you should always be aware that they are available to you. So now if I want to solve for what is the direction of the electric field, well, E is simply equal to F divided by Q. So equals to, in this case, you end up with, I'll put this in red, 1.56 times 10 to the 15th newtons per coulomb. Okay? But what's the direction? Well, positive charges always feel a force in the same direction as E. So in this case, the electric field will probably be pointing in this direction. So it's going to be to the left. Now, if you have trouble imagining what that looks like, sometimes it helps to draw out what the parallel plates look like. So in this case over here, we know that the proton is moving to the left. So that means there's going to be a parallel plate over here and a parallel plate over here. Well, what charge is a proton attracted to? Of course, it's attracted to a negative charge, which means that this is a negative plate over there, a positive plate over there, and electric fields always go out of positive and into negative. So if you need to just take your time to work it out, logically it should make sense that the electric field is in the same direction as the force. Now, because we know the force, we should also be able to solve for the acceleration of the proton. That means acceleration is equal to force divided by mass, 2.5 times 10 to the negative 4 newtons divided by 1.67 times 10 to the negative 27 kilograms, 1.5 times 10 to the 23rd meters per second squared. Now you might be thinking that's a huge number, and you're right, that's a gigantic number. But it's not impossible. You might be recalling from waves that nothing can travel faster than the speed of light. Nothing can go faster than 3 times 10 to the 8th meters per second. But even though my acceleration is this large, we never actually say what the final speed is. The fact is that the proton will accelerate, but it won't have enough time or enough space to reach that high of a speed. We try this again with an electron. An electron experiences a force of 0.06 newtons to the right. So here's my electron, which of course I know is a negative charge, feels a force to the right of 0.06 newtons. What is electric field? Well, because it is an electron, I should also automatically know the charge of electron is 1.6 times 10 to the negative 19 coulombs. Charge signs don't really matter. I don't use them in my formulas. The mass of electron is restated over here as 9.11 times 10 to the negative 31 kilograms. Again, both of these are also on your reference table. So if I want to solve for the electric field on an electron, I would simply do E equals to F over Q, so 0.06 newtons divided by 1.6 times 10 to the negative 19 coulombs, 3.75 times 10 to the 17th newtons per coulomb. But what's the direction? Now, you can hopefully remember that negative charges always feel a force in the opposite direction of the electric field. But if you can't remember that, just remember to draw in parallel plates. Negative charges are always attracted towards positive charges, so that left plate has to be positive. The right plate has to be positive. Left plate has to be negative. So therefore, the electric field points to the left. So the answer is left. Now, why is it so important to be able to accelerate electrons from one plate to the next? Well, here is something called an electron gun. And even though that gives you all sorts of misconceptions probably, the fact is this electron gun is the basis for all of our original TVs. I'm not talking about the flat screens. I'm talking about those big box sets, right? The Trinitron tubes, the CRTs. They're called Cathode Ray Tubes. And with these CRTs, you'd actually have inside basically a parallel plate where a cathode gives off electrons, which are then accelerated towards the positive plate, and they're shot towards the TV screen. We have to look at, let's say, this model over here. So basically, we can see that there's an electron being shot out. We have our parallel plates over here. Here's a negative plate. Here's a positive plate. And the electron is shot, and on the other side would be the TV screen. So, of course, since we are able to do all sorts of mechanics questions on this, this could be a negative charge or a positive charge. Let's do some practice question with this now. A particle with a mass of 1 times 10 to the negative 3rd kilograms has an excess charge of positive 1 microcoulomb. So 1 microcoulomb means 1 times 10 to the negative 6 coulombs. And the electric field that exists there has a magnitude of 1,000 newtons per coulomb. They ask us, what is the force acting on the particle? What is the acceleration? And if the distance is 0.01 meters, what is the final velocity right before it strikes the other side? In this case, we are neglecting gravity, and we have our one force accelerating it to the right. So the electrostatic force is equal to Q times E, so it's 1 times 10 to the negative 6 coulombs times 1,000 newtons per coulomb. And you get that the Fe is equal to 0.001 newtons. And once you know the electrostatic force, you can set that equal to ma. Okay? And so if you start with acceleration, a is equal to 0.001 newtons divided by, they give us a mass of 0.001 kilograms. In this case, it equals to 1 meter per second squared. Now, if I'm looking for a distance, if I know the distance, I'm looking for final velocity. The initial velocity, of course, would be 0. I could use v squared equals VO squared plus 2a delta x. So final velocity is equal radical 2a delta x, 0.14 meters per second. Okay. Now this speed happens to be very low, but in reality, these charges are shot at near light speeds. And we can calculate, of course, what their speed is always going to be. Now the thing is, I have a picture of an electron gun here. And how do you actually get the electron to strike the screen of the TV? Because it's a large screen, and these electrons are shooting straight. Well, part of the way they're able to do so is with these vertical plates. That's only step 1 of the equation, which is what we're going to talk about. But because we have another set of parallel plates inside, it's able to deflect the electron to a different location. Let's take a look at here. We still have the same electron shooting straight. But now take a look at what happens if I increase the voltage on the plate. So you guys can see that there's a voltage now on the plate. And if I shoot the electron, the electron's attracted towards the positive plate. Okay, it's actually deflected to a different location on the screen. If I reverse the voltage on the plates, making the top negative and the bottom positive, in this case over here, now when the electron shoots through, it's going to be attracted towards the bottom plate. And again, we can have the electron strike a different location. So how do we calculate this deflection? Well, first thing I would like to comment on is notice this parabolic shape that this electron is falling through. Where else have we seen parabolas before? And the answer, of course, is projectile motion. So this actually becomes a projectile motion question. So over here, I think the only information I accidentally left out was that the distance between the plates was 0.5 meters. Okay, we have an electron shot at an incredibly high speed of 3 times 10 to the 7th meters per second. There's an electric field inside with a strength of 20,000 newtons per coulomb. They say to neglect gravity, and we'll explain why later on. So when the electron actually travels through, the question is, in which direction does it feel a force? Because the charge is positive up there, it's going to feel a force upwards of QE. And the QE, we can always set equal to mass times acceleration. So when we're solving for the acceleration of the electron, acceleration is equal to Q times E divided by M. So that's 1.6 times 10 to negative 19 coulombs times 20,000 newtons per coulomb divided by the mass of the electron, which we had previously stated to be 9.11 times 10 to negative 31 kilograms. When you plug this in, you get the acceleration to be incredibly high, 3.51 times 10 to the 15th meters per second squared. Now, the only reason we're able to neglect gravity here, the fact is there is gravity. I'm going to talk about that now briefly. I'm going to erase it in a moment, but there is a gravitational force of mg. But what is the acceleration of gravity? 9.8. And how is that compared to this acceleration over here? It's insignificantly small. So that's why we're always going to be able to neglect gravity whenever we have a projectile motion question like this. Now the thing is, the acceleration is 3.51 times 10 to the 15th, but it's on the y-axis. The electron's moving on the x-axis. And it's going to veer upwards. Our question is, by what value, by how much does it veer upwards? So we have to solve for delta y. So in order to solve for delta y, we need to make an xy chart. The acceleration on the y-axis is 3.51 times 10 to the 15th. Acceleration on the x-axis is equal to 0. The initial velocity on the y was equal to 0. Initial velocity on the x-axis was 3 times 10 to the 7th. We know the distance it travels forward is half a meter. We're looking for delta y. So what do we solve for first? Well, in this case, because it is basically like the cliff problem, we know that the time on the y-axis will equal to the time on the x-axis. Can't use the y-axis to solve for time because we don't know what delta y is. However, we do have enough information on the x-axis. As v bar is basically equal to delta x over t, t will equal to delta x over the initial velocity. In this case over here, you get 0.5 meters divided by 3 times 10 to the 7th. Which equals to 1.67 times 10 to negative 8 seconds. So this time in here is also 1.67 times 10 to the negative 8 seconds. And to finish off, we know that delta y is equal to 1/2 at squared because of the fact that VOT crosses out. You get 0.49 meters. Okay, so yes, I know this is a projectile motion question, but luckily it's very straightforward.